let's look at this pig diet problem. So a pig needs 200 units of carbs and 180 units of protein per day. And there's two types of feed, corn and alfalfa, and we can mix any amount of either feed to get the pig the total nutrients needed. So the corn has 100 units of carbs per kilogram, 30 units of protein per kilogram. Alfalfa has 40 units of carbs per kilogram, 60 units of protein per kilogram. Currently, they each cost 30 cents per kilogram. We'd like to minimize the total price of the feed. Okay, so to solve this, we'll let C be the kilograms of corn that we're going to use, and A be the kilograms of alfalfa that we're going to use. And we'd like to minimize, we could multiply them both by 30 and add them together, or we're really just minimizing C plus A. Okay, and then we have some constraints, which we can write as inequalities. So 100 corn plus 40 alfalfa is the total number of carbs, and that has to be at least 200. And then we have 30 corn plus 60 alfalfa is the total amount of protein, and that has to be at least 180. And we can scale these down. Divide both sides of this one by 20, so 5c plus 2a greater than or equal to 10. Divide both sides of this one by 30, c plus 2a is greater than or equal to 6. Okay, and now instead of using completely our archaic methods from before, we're going to graph these inequalities so that we have something to reference. Let's make this the corn axis, this the alfalfa axis, and let's see, what do we have? The y-intercept here is 5. We'll just make these each worth 1. That's 5. And the x-intercept is 10 divided by 5 is 2. See how much faster this is than converting to slope-intercept form. Okay, there's that line. And then here, the y-intercept, or the a-intercept, is 3, and the c-intercept is 6. If I only label 2 numbers on each axis, then everything else is determined, so the 0 counts. Okay, great. So there it is. Let's solve for the point of intersection, which is this point. Okay, so we'll convert these two equations. 5c plus 2a is 10, c plus 2a is 6, equation 1, equation 2. We'll just take 1 minus 2, get 4c is 4, so c is 1. Sub that into 2, 1 plus 2a is 6. Solve, we get a is 5 halves, or 2.5. Doesn't really matter in this case. Okay, so this point of intersection, which again I have not drawn perfectly, is 1 comma 2.5. And let's just try to shade this. Right now we're greater than. So for example, like the origin would not satisfy either of these inequalities. 0 is not greater than or equal to 200. So we're on the other side of the origin. So actually, and we also need, of course, c and a to be greater than or equal to 0. So we're still all in the first quadrant. We've got that region, which, by the way, we call the feasible region. Okay. Then, what is our actual optimum? Let's draw this gradient vector. So, pretty easy here. The gradient is 1, 1. So we're going to go exactly at 45 degrees. That vector, let's look at these level curves. And actually, we're coming this way this time. So we've got level curves here, here, and then the last one to touch the feasible region does look like it goes through that point and only that point. So that looks like that'll minimize the cost. So t is going to be 3.5, and then multiply that by 30 cents. Okay. What if we change the problem now? We're going to change alfalfa to be $1 per kilogram. Okay, what does that change? This means now, we'll still call it t, but now we need 30 cents and $1. That's just a 3 to 10 ratio, so I'm going to call it 3c plus 10a. If we multiply it by 10, we get the cost in cents. Okay, so now my gradient is going to be 3 comma 10, that vector. Okay, what happens though? That vector is much more vertical than the vector 1, 1. Right, that goes, see, 3 comma 10 is up there, so it goes towards there. Now what happens? We have these level curves. We're here. As we go through this point, that's pretty almost horizontal level curve. And the rest of the curve is still in the region. This is not the last point. So we can keep drawing these. We're still intersecting the region. And here then, the last level curve will touch the region at that point. So this is the first time we see this point of intersection is not the solution. Here we've got this point, which is 6 comma 0. Let's just check this t of CA. We'll write this as a function so we can be clear on what we're plugging in. T of 1 comma 2.5 would have been 3 plus 25 is 28. T of 6, 0 is 18 plus 0 is 18. So indeed, this all corn solution, when alfalfa is too expensive, makes our total cost cheaper. Total cost is this times 10 in cents. Okay, let's change one more thing. What if we now made alfalfa 60 cents per kilogram? Okay, then alfalfa's double the cost, so we're going to make t double the cost of corn. So t is c plus 2a. Our gradient is now 1 comma 2. Okay, let's see what happens to this. We're going to get 1 comma 2. There's too many lines on this, but it looks like this. There's our vector. So that's like a slope of 2. Notice that this line that we've drawn has a slope of negative 1/2. Right, slope is negative b over a, so this is slope negative 1/2. It's always been slope negative 1/2. This is not particular to the orange number. So this line is actually one of the level curves. What does that mean? That means that that's the last thing to hit, because everything over here is still in the region. Everything beyond this line is outside the region. So that means everything on this line should minimize our t. Let's just check these two endpoints on the line, but really anything in between will too. So now we have t of c comma a is c plus 2a. T of 1 comma 2.5. Let's check that. 1 plus 2.5 times 2 is 5 is 6. And t of 6, 0 is, of course, 6 plus 0 is 6. So those both work, and actually anything in between will also give that same minimum value of 6. So that was pretty exciting. That's the first problem where that point of intersection where we just assumed the inequalities were equations was not the optimal solution. But we noticed that the optimal solution was always one of the corners of that feasible region. And it's always, for two variables at least, it's always going to have three corners. Is that always true? It should be, because think about those level curves. The level curves are lines. Lines are always going to last touch a region, basically polygon, but maybe unbounded polygon region. The last touching point is always going to be a corner. So your answer is always going to be one of those corners, and we can just check the corners, which for two variables is pretty easy.